Scientists have put forth a new theory about the reason behind the comet that took the life of the dinosaurs. This new theory explains the possible origin of the Chicxulub impactor. It was tens of miles wide and forever changed history when it crashed into Earth about 66 million years ago. The Chicxulub impactor, as it is known, left behind a crater off the coast of Mexico that spans 93 miles and goes up to 12 miles deep. Its devastating impact brought the reign of the dinosaurs to an abrupt end, and it triggered their sudden mass extinction, along with the end of almost 3/4 of the plant and animal life on Earth. This enduring conundrum has always been where the asteroid or comet that set off the destruction originated and how it came to hit the Earth. And now a pair of researchers believe that they have found the answer. As an astrophysics concentrator, they have put forth a new theory that could explain the origin and journey of this catastrophic object and others similar to it. Through the use of statistical analyses and gravitational simulations, these two researchers have indicated that a significant fraction of a type of comet which originated from the Oort cloud, a sphere of debris at the edge of our solar system, was bumped off course by Jupiter's gravitational field during its orbit and was sent close to the Sun, whose tidal force broke apart pieces of the rock. That increases the rate of comets like Chicxulub, because these fragments across the Earth's orbit would hit the planet once every 250 to 730 million years or so. Basically, the researchers theorized that Jupiter acts as a kind of pinball machine. He further went on to explain that Jupiter kicks those incoming long-period comets into orbits that bring them very close to the Sun. It is because of this that long-period comets, which take more than 200 years to orbit the Sun, are called sun grazers. When you have these sun grazers, it's not so much the melting that goes on, which is a pretty small fraction relative to the total mass, but the comet is so close to the Sun that the part that's closer to the Sun feels a stronger gravitational pull than the part that is farther away from the Sun. This results in a tidal force, which ends up with you getting what's called a tidal disruption event. So these large comets that come really close to the Sun break up into smaller comets, and basically on their way out, there's a statistical chance that these smaller comets will hit the Earth. The calculations and studies that were done by these two researchers indicate that their theory will increase the chances of long-period comets impacting Earth by a factor of 10. And it also indicates that about 20% of long-period comets become sun grazers. That discovery falls in line with research from other astronomers. These two researchers claim that their new rate of impact is consistent with the age of Chicxulub and provides a satisfactory explanation for its origin and other impactors similar to it. The research provides a basis for explaining the occurrence of this event. They are suggesting that, in fact, if you break up an object as it comes close to the Sun, it could give rise to the appropriate event rate and also the kind of impact that took out the life of the dinosaurs. They are also stating that their hypothesis might also explain the makeup of many of these impactors. Their hypothesis predicts that other Chicxulub-sized craters on Earth are more likely to correspond to an impactor with a primitive or carbonaceous chondrite composition that is expected from the conventional main belt asteroids. This is important because a popular theory on the origin of Chicxulub claims that the impactor is a fragment of a much larger asteroid that came from the main belt, which is an asteroid population between the orbit of Jupiter and Mars. Only about a tenth of all main belt asteroids have a composition of carbonaceous chondrite, While this assumed most long-period comets have it, evidence have found that Chicxulub crater and other similar craters suggest that they are of a carbonaceous chondrite origin and composition. This includes an object that hit about 2 billion years ago and left the Vidrite crater in South Africa, which is the largest formed crater in Earth's history, and the impactor that left the Zamashin crater in Kazakhstan, which is the largest confirmed crater within the last million years. According to researchers, the composition evidence supports their model, and that they also state that the years the objects hit support both their calculations on impact rates of Chicxulub-sized tidally disrupted comets, and for smaller ones like the impactor that made the Zamashin crater. If produced in a similar way, they say these would strike Earth once every 250,000 to 730,000 years. They have stated their hypothesis can be tested by further studying these craters, others like them, and even ones on the surface of the moon to determine the composition of these impactors. Space missions sampling comets can also assist in further research. Like, comment, share, and subscribe. Of course, these astronomers are fascinated by the composition of comets, and they believe that the new Vera Rubin Observatory in Chile may be able to see the tidal disruption of long-period comets after it becomes operational next year. Of course, they are aiming to see smaller fragments coming to Earth more frequently from the Oort cloud. They hope that they can test the theory by having more data on long-period comets, get better statistics, and perhaps see evidence for some fragments. They are closer to solving this critical mystery that lies in Earth's history. But of course, they need to do further work. Thanks for watching. Goodbye.